Hi, and welcome to my session, Oracle Parallel Execution Plans Deep Dive. My name is Eberle-Geist. I'm an independent consultant, also book author, member of the Oracle ACE program as an Oracle ACE director, and also member of the Oak Table network. Contributions: where can you get content published by me? Primarily on my blog, where I regularly publish things that I find noteworthy to communicate, but you can also find some video tutorials on my YouTube channel, and I also from time to time try to answer questions on the OTN forums in the database part, so if you raise questions there I might try to address them. So what is this session about today? Oracle Database Parallel Execution Plans Deep Dive, understanding the internals of parallel execution plans. And if you are interested in more information on that topic after this session, you can check my blog. I have these labels there where you can search for notes labeled with parallel execution, and also check my YouTube channel where I have lots of video tutorials covering all this parallel execution stuff in more depth. Also, I offer a parallel execution masterclass, so in 1 or 2 days I can give you really a deep insight these parallel execution stuff. If you are making regular use of it or want to make use of it, plan to make use of it, and want to get a better understanding what you can do, what you can't do, what are the traps and pitfalls, then I can highly recommend this parallel execution masterclass seminar. So, what is the goal of this session? Well, basically, if we look at a serial execution plan like this here, it's a very simple, trivial one. So it's just a two-table join using a hash join. And how does this operate? Well, the hash join first reads the data that comes from this first row source, this table access full, builds the in-memory hash table, basically builds on the fly a hash cluster in memory. Hopefully, if it doesn't fit into memory, it might spill to disk. And then when this is completely consumed, when this is completely done, and the hash table is available, then it starts actually reading from the second row source, in this case here, this table access full of the table T2, and whatever data is identified there will then be again consumed by the hash join, and it will perform the actual hash join, the actual join operation by doing this hash lookup into these in-memory tables, and any matching rows will then hand it over to the parent operation, which in this case is simply the root operation. So these are the rows basically that will then be returned to the client. So this is a simple two-table join using serial execution. And if we look at the corresponding execution plan, more or less doing the same using parallel execution, you will notice there is a lot more in this execution plan. There are more operations and there are even more columns available. And basically all I've highlighted here in red with these red boxes, all of this is not there in the serial execution plan, which means there's actually more that is highlighted in red than is not highlighted in red. So we can see this looks far more complex. At the end of this session, I would like to have you a rough idea what all these things that are marked here in red are about, so that you have at least a rough idea why is this there and what is the purpose of these additional operations, and where you might then can find more information about these things. Okay, so in order to understand these things, let's start with how does Oracle actually execute things in parallel. One possible theory could be that it starts to run unrelated operations at the same time. For example, it could run this table access full here, and maybe this table access full, and also this table access full at the same time. And this would also be some kind of parallel execution, but this is not the way it usually works with Oracle Parallel Execution. There is one exception to this rule actually that was introduced with Oracle 12c. There is a new operator that is called Concurrent Union All. So Oracle 12c can actually run different unrelated branches of a union all operation. So it actually follows this running multiple unrelated operations at the same time pattern, but this is more or less an exception to this rule. So this is the special case concurrent union all. If you want to understand more about this, how this actually works, I had a deeper look, closer look at this feature on my blog. I have published 3 parts where I give you more details if you want to get more understanding of this concurrent union all feature. But with this exception, in general, it works like this. Oracle parallel execution starts where the data access happens, so at the leaves of the execution plan. So in principle, Oracle then uses a single operation of the execution plan and starts running this in multiple sessions, in multiple processes, which means that it tries to split the operation up into multiple pieces, in multiple chunks, and each of these different sessions then actually work on these smaller pieces of this operation, and they run at the same time. So rather having a single process running this table access full, we now end up with multiple processes, multiple sessions that are running this full table scan here. And this is indicated, and this is the purpose of this PX block iterator, that it basically divides this table access full into multiple chunks, and each chunk is then assigned to a so-called parallel execution server, or sometimes they are also called parallel slaves. So each session then works on its own chunk, and once this chunk is done, the next chunk gets assigned. So this is in principle how Oracle parallel execution works. It doesn't start unrelated operations at the same time, multiple ones, but it starts a single operation and then spawns multiple sessions that work on different pieces of this single operation. And there are actually 2 different ways how this splitting of things into multiple pieces can work. The most common one is this dynamic one, which is called PX block iterator, which means that basically Oracle divides one segment dynamically into multiple chunks of same size. So that's basically block ranges from starting from this block to this block, or maybe even row ID ranges starting from this row ID to that row ID is one chunk, and so on. And the other way how things could be split into things is if you work with Oracle partitioning, then you can also have these parallel slaves working on partition levels. So each parallel slave works on one partition, and once the partition is processed, and if there are still partitions left, then it will get the next partition and work on that partition. One thing that I just want to briefly mention, but it's a very important topic if you deal with parallel execution, is the work distribution. You only gain really benefit from parallel execution if you manage to give all of the sessions involved more or less the same amount of work, and you're able to split the thing that you want to process in parallel into pieces of similar size, and have a high enough number of pieces so that each parallel slave can be kept busy. As I indicate with this picture here, for example, with partitions, you might have the issue that the partition is not of the same size, and then you might have an imbalance between the different parallel slaves. So one of these slaves might work on a much larger partition than the other parallel slaves, and so it might take much longer for it to complete, while the others are already done with the smaller partitions, and then basically the operation has to wait until this last parallel slave is then done with that processing of that larger partition. So this work distribution is a common topic when you deal with parallel execution, and there are various ways how this imbalance, this uneven distribution might happen. And if you're interested in those things, I have more information available again on my blog, and also in these video tutorials where I explain this issue and maybe even what you can do about it. So for more complex operations, Oracle has to do more complex things. So for example, if we think about joins or aggregates or sorts, then Oracle cannot use this simple I divide things into multiple chunks approach. It starts with that at the data access layer, But then, as I said, for more complex operations, Oracle has to ensure that there is some deterministic behavior in terms of which rows get processed by which parallel slave process. So this one here is a simple and good approach, which usually should ensure that you have this even work distribution, because the segment is divided into this equally sized pieces. And then we come to this point that as I said, and since basically each parallel slave picks up some chunk and then takes the next chunk to process once it's done with it, it's really a kind of random distribution. So it's not really deterministic which parallel slave works on which chunk and on which piece and which rows will be processed by what parallel slave. But for more complex operations like joins, you can no longer follow this pattern. For efficiency and correctness reasons, Oracle has to ensure that there is some deterministic way how the data gets processed. Therefore, in such a case, Oracle has to redistribute the data among these parallel slaves. And whenever you have this redistribution happen, then Oracle uses this so-called producer-consumer model, where basically one part is producing the data, sending the data, and another part is basically receiving and consuming the data. That is this producer-consumer model. This also means that whenever you have this redistribution of data in your execution plans, there are actually two sets of parallel slaves, because one set is basically doing this, is basically producing this data, and one set is basically receiving the data. So that's another important point. If you, for instance, operate at a degree of 8 and you have these redistributions in your execution plan, you end up with two sets of 8 parallel slaves, which means that there are actually 16 parallel slaves that might be active at the same time, one producing, one consuming the data. Also, in terms of reading this execution plans, we come to another term in this context, which is a so-called data flow operation, which gets abbreviated DFO. So this producer-consumer model then, in terms of reading the execution plan, is implemented via so-called child data flow operation, which is performing this producing the data, and we have this parent data flow operation, which is running this consuming, this receiving of the data. So these are the two sets. And one set, the set that is producing the data is the child DFO, child data flow operation, and the other one consuming the data is the parent data flow operation. We come later to that again when we look at the execution plans. Also, the infrastructure, the construct that gets used by Oracle to exchange this data, to send and receive the data between these two sets, is called a table queue, and sometimes also called virtual table. So this is a kind of in-memory construct, a message pool that gets allocated from the shared pool or from the large pool, where data gets then exchanged and corresponding buffers get allocated in this pool, and then basically the one set puts data into these buffers and the other set receives the data by accessing these buffers with the data. If you think about, this is true for single instance, if you think about a cluster database, so if you have multiple instances, then this table queues also, of course, involve then network traffic, because the data might have to be exchanged between these different instances. So both of this in this memory operation, or then of course even more particular the network operation, means that if you have to exchange a large amount of data like gigabytes, terabytes or petabytes, then of course this is not a no cost operation. This of course costs time and CPU resources or even network resources to exchange that data. So this is one reason why if you deal with parallel execution, then this operation, this redistribution of data, is something that is simply not there with serial execution. So with parallel execution, you typically have to work more and harder than with serial execution, because there are things involved that are simply not necessary and simply not there with serial execution. So this is overhead that comes with parallel execution. There are ways how this overhead might be possible to minimize. There are the so-called partition-wise operations, which can be very efficient. They can be used for serial execution, but in particular for parallel execution, this partition-wise operations can help to minimize this kind of overhead. But if you can't perform these partition-wise operations, then you basically need to have these redistributions taking place depending on what you do. And this is just overhead that comes with parallel execution. So we have this producer-consumer model, which means that the execution plan reflects this by being organized in so-called data flow operations, child and parent data flow operations. And these data flow operations in turn are then organized in so-called DFO trees. So one DFO tree consists of one or more of these data flow operations. There can be many data flow operations as part of this DFO tree. And I will come later to this DFO tree because these DFO trees can have some significant side effects that you need to be aware of if you want to deal with parallel execution and understand what is going on. So, and of course, this producer-consumer model also requires these two parallel execution slave sets so that they can talk to each other. So if we now return to our parallel execution plan, what exactly does this mean and how can you read this? How is this working with this child and parent data flow operation and this table queues and this exchange, this redistribution of the data? So again, this is a simple two-table join, and it starts with this table access full, in this case here with this T3. So we have here multiple parallel slaves that work on multiple chunks of this T3 table. Whatever data they produce in this full table scan, they now produce this data and send it via this table queue here to the other data flow operation, to the other parallel slave set. And you can see here that we have these numbers here after the comma. So we have this 00 here, 00. And basically this column TQ here is there so that you can get an understanding which operations belong to the same data flow operation, which means they are executed by the same parallel slave set. And whenever you see then a different number here, this means that the data will have to be redistributed, will be sent and received in order to arrive at the other parallel slave set, the other data flow operation. So we have here this table access full. It runs this parallel full table scan. Each parallel slave then sends this data that it identifies in the full table scan to the other parallel slave set via this table queue that the other slave set consumes, receives this data. You can see here they are marked with this 02 and basically runs then this hash join, which means for any data that it receives, it builds this in-memory hash table. So the basic functionality is the same as in the serial execution plan, but it is done in parallel. So multiple sessions are working, maintaining multiple of these in-memory hash tables. Ideally, if it's not possible to keep them in memory, that will spill to disk. Of course, it's the same as with the serial execution. It's important to understand that there is no deeper meaning in this numbering here behind the comma, so you don't have to expect that here 00 talks to 01 and then 01 talks to 002. As you can see here, the sequence is basically defined by the plan shape. So this child data flow operation here, these 00 actually in this case talks then to this 02. And then we will see in another step how this works when we continue. But the important point to understand is this one parallel slave set is working on this DFO, producing the data. One parallel slave set is working on this part here, receiving the data and building these hash tables. It's also important to understand that this hash distribution here is not necessarily related to the hash join. This could also be a parallel merge join. Still, the data would be distributed via hash. So it's just that they both basically, the underlying mechanism used to run this operation is a hash function. So, but a hash join doesn't have necessarily to have a send hash operation. So this is independent from each other. There are different distribution methods available for parallel execution. So there's also a broadcast distribution or a range distribution or even a round robin distribution for cases where the order, the sequence doesn't matter. So depending on what actually Oracle needs to do, it automatically chooses some distribution method, and some of them you can also influence via hints. So this is also possible. And this column here in the to the right hand side here, this is one is more or less, well, let's say it's just, I think there for historic reasons, it doesn't really give that much information that you can't derive from the other information, but just to give you an idea what these abbreviations here stand for. This is just parallel combined with parent, PZWP, and parallel combined with child. So it's just another way to express that these operations are basically performed by the same parallel slave set, and whenever data needs to be sent, redistributed, then you see this parallel to parallel, or maybe sometimes also parallel to serial, or the other way around, serial to parallel. This is all possible because you could also have serial parts of your execution plan. So you can have a mixture of parallel operations and serial operations, and this is then what this here expresses, that the data gets distributed from the parallel part to the serial part, or the other way around, from the serial part to the parallel part, or if it's from parallel to parallel, then it's parallel to parallel. But apart from that, it's not really that giving that much more information. So when this operation here is done, it's following the same principle than the serial operation. So this hash join has to consume all the data that is coming from this full table scan, but we have this redistribution here in between. So this is done by one parallel slave set. This is done by another parallel slave set. Once this is done, we come to the second phase of the hash join, which then basically means that we see here that still this parallel slave set here that has performed this first phase of the hash join, which has received this data here, is now still performing this part of this operation here, because it's still marked, highlighted with this O2. So it's the same parallel slave set, and you see here also this O2. So this second receive operation is also performed by the slave set that has performed this receive operation here in the first phase. And then we have this parallel slave set that has done this part, has run this child data flow operation. When this is done here, when this is completed, it will basically start this operation here. This child DFO, which is marked with this O1, will be started next. We have another table queue here that will be used to exchange the data again between this child data flow operation operated by the same parallel slave set that did this thing here, and it will be sent to the parallel slave set that still did receive the data here, which makes sense because these are the sessions that have already built this in-memory hash tables. So they have to, in order to perform this join, the same parallel slave set needs to receive now the data in order to perform the actual join operation. So again, this follows the same pattern. We have this parallel operation here. So multiple processes work on different pieces of this full table scan. Whatever data they identify, they hand over via this table queue to the other parallel slave set running this second phase of this hash join. And if we had the same pattern than we had for the serial execution, then we were now at this phase where the actual join would be performed. So the hash lookup would be performed in memory in these in-memory hash clusters, and any matches, any join results would then be handed over here, in this case, to the query coordinator via this pxsend QC query coordinator operation, which basically means handing over the data, in this case, then to the client, which is the same that as you have with the serial execution. But we have here this buffered keyword, and there's a limitation that I will come to later with parallel execution, which means that at this phase, this here actually does not perform the actual join operation, but it actually just receives the data and puts it aside. So this is another limitation or additional overhead that you have with parallel execution, that you have these buffered operations. And that's just to give you an idea that things work a bit differently with parallel execution, and I will come to that later. Now let's first focus on this DFO tree thing. So how does this DFO tree, this term, what does it mean? What does it stand for? So a DFO tree, as I said, basically is the parent, is the tree that represents these multiple child and parent data flow operations. So as you've just seen here, we have this multiple child and parent data flow operations, and they all belong to the same DFO tree because they are all below the same PX coordinator. So whenever you want to get an understanding, where does this DFO tree start? It's very simple. The PX coordinator operation is the root node of this DFO tree, and below this PX coordinator there will then be one or many of these data flow operations. You can also identify these different DFO trees if there are multiple ones by this what is here before the comma. So what is in front of the comma, this Q1, basically identifies the DFO tree number 1. This is also reflected in this TQ1, which you see here. So this is basically the same information again, which means all these operations belong to the same DFO tree. The most parallel execution plans actually consist only of a single DFO tree. So in that case, you can actually ignore the fact that there is something like a DFO tree because it doesn't really matter. But it's possible to end up with parallel execution plans where you actually have multiple of these DFO trees, which you can see here. So we have here this Q1 DFO tree. We have here a PX coordinator. We have this Q2 here. We have again a PX coordinator. And above here we have also a PX coordinator, which is then Q3. So in this case, you can see here that this all fits together. So this is just a limitation of the optimizer. So depending on what operations, plan operations, SQL features you make use of, it might decompose a parallel execution plan into multiple DFO trees. And this has several side effects that you need to be aware of, and that's the reason why I mention it here, because it's probably more confusing than helpful in first place, but it's a deep dive session, so you should be aware of what these DFO trees are about and what the side effects, the possible side effects are. One thing is that basically in terms of parallel execution, each DFO tree is optimized as a separate unit by the optimizer. Also, each DFO tree gets its own parallel slave sets assigned, which means that this DFO tree here, which does this redistribution here, gets 2 slave sets because data gets redistributed. So there has to be one producer and one consumer, one child DFO, one parent DFO. And we have here another DFO tree, which again gets parallel slave set assigned, since we do not have a redistribution here. So we do not have really another slave set that receives the data, because it only redistributes the data to the query coordinator. It will only get assigned a single parallel slave set. But still we might end up here with actually 3 parallel slave sets that might be active at the same time. So that is one important side effect that these multiple DFO trees might have, that you actually end up with more parallel slaves allocated than you might expect. So there can be more than 2 sets active at the same time. But this is only possible if you have multiple DFO trees. For one DFO tree, you have at most 2 parallel slave sets active doing this producing and consuming of data. But since you can have multiple DFO trees and each DFO tree has its own parallel slave sets assigned, you might actually end up with more parallel slave sets active and allocated at the same time than expected. This is one important point. Another important point is also related to this fact is that since each unit is optimized, handled separately, each DFO tree, this also means that each DFO tree might run at a different parallel degree, which might be even more confusing, which means that for a single parallel execution plan, you actually might have multiple different degrees. So this part here of the parallel execution plan might run at a different degree than this part here of the execution plan, because each unit gets its own parallel slave sets assigned. So these here just might run at a degree of 4, this might run at a degree of 8 or whatever. So this is another important side effect of these DFO trees, that things might run at a different degree. So this can be quite confusing, and there's another reason why you probably want to have only a single DFO tree parallel execution plan, but in reality it's possible to end up with things like what I just show here. So it's possible to have multiple DFO trees, and it's possible to run into this situation with these different degrees used in a single parallel plan. So in order to give you an idea that it's just not theory that I'm talking about, but this can happen in reality, and also to give you some idea where all these terms come from. Why? Because one of the problems that we have with parallel execution is that all these things that I've mentioned, data flow operations, data flow operation trees, table queues, virtual tables, all these terms are actually, at least as far as I know, they are not officially documented. So you don't find an official document by Oracle that actually explains what these things stand for. But as you can see here, for example, here in this real-time signal monitoring report, so if you happen to have a diagnostic and tuning pack license, you can make use of this real-time signal monitoring, which is a very, very good way to deal with parallel execution. You can find here, at least in version 12c, you find here these terms like parent DFO and child DFO mentioned in the report. So it's there. These terms get used. Also, if you use this PX trace facility, you will also find these terms like parallel slave and data flow operations and DFO trees and things like that might be mentioned there. So although it's not officially mentioned by Oracle, at least here at some places these things pop up, and that's the reason why I explain it. Also, you can see here just an example. In this case here, unfortunately, Oracle has invented another term. Instead of DFO tree, they call it now parallel group. Here in this real-time signal monitoring, don't ask me why. I think it's the only place where I have seen this parallel group term. But as far as I understand, parallel group stands for DFO tree. So we have here this DFO tree number 1, which has 2 slave sets, and each slave set consists of the same number of slaves. So we have 2 slave sets, and each slave set consists of 16. So this DFO tree operates at a degree of 16. But then going further down, we have this DFO tree number 2, which then actually operates at a degree of 4. So this is the same parallel execution plan, and we actually have these multiple DFO trees, and each DFO tree can actually operate at a different degree, gets its own parallel slave sets, which is also reflected in this real-time signal monitoring report. You can also see this here confirmed, that these operations here are all executed 16 times. There are operations that are operated more times due to this chunking. So as many chunks as there are, as many times this gets executed. Like this here gets executed where there were 202 chunks created dynamically. But you can see here that these operations are then executed only 4 times. So this is this other DFO tree, this PX coordinator, which indicates this is the root node of another DFO tree. And it actually ran at a different degree. So this is actually possible. And also real-time signal monitoring doesn't really do a good job to tell you about this. It only tells you the maximum degree found in the plan. So it tells you here this was run at a degree of 16, which is not the entire truth, because we have parts of the execution plan that were executed at a degree of 4. So just to have you shown this with a real-life example. In Oracle 12c, well, with this multiple DFO trees, this has been like this for a very long time. And in Oracle 12c, Oracle introduced some new features that allow to simplify things. So more plans that in the past were decomposed into multiple DFO trees in 12c will now be treated as a single unit, so you end up with a single DFO tree, which is a good thing because all these complexities like different different number of parallel slave sets, different degrees, and so on, all these things are gone. When you have a single DFO tree, you can simply ignore this. So this is the same execution plan in principle that we have here, which is decomposed into 3 DFO trees in pre-12c. In 12c, it will be a single DFO tree, and it introduces also some new parallel features that I also mentioned on my blog. For example, this px send one slave is one of the things that 12c uses in order to merge everything into a single DFO tree. And we come also to this odd things here with 12c, where it's actually serial combined with child and serial combined with parent, which means that this part here, although it looks like a parallel execution, is in reality executed by one of these parallel slaves. That is what is the meaning of this send one slave, which means that one slave receives all the data. So in Oracle in pre-12c, the query coordinator process, which is the one that you usually use for your serial execution, would be the one that operates these operations here. And in 12c, it will be one of the slaves instead of the query coordinator, which then gives this serial part here. So we have a serial part here, which looks like parallel. So you have to look very closely at this here. Yeah, in this case, maybe this is an important information that you have this parallel and serial combined with parent indicated by this column, so that you get a better understanding that this, although it looks like a parallel operation, is actually a serialized operation performed by one of the parallel slaves. I won't go into more details. If you want to have more details about all these different plan shapes and DFO trees, then as I said, you can watch these video tutorials and read the blog notes on my blog where I provide more details. So finally, this limitation that I have mentioned. So there is this problem that this producer-consumer model that Oracle implements comes with a significant limitation. Very simply spoken, very trying to express it very in an easy way, is that only one of these redistributions, one of these send-receive pairs, these child and parent DFO pairs, can be active at the same time. But as I've just outlined, if you follow the plan shape, then in principle multiple of these operations, these redistribution operations, would have to be active at the same time. But this is simply not possible, at least up to including 12.1. Oracle does not allow this. It's not implemented, so it has to introduce something, some artificial operation that prevents that multiple of these operations get active at the same time. I know that Oracle has internally discussed this, whether they want to address this issue or not, and maybe in 12.2 we already see some changes regarding that, but I didn't have a chance yet to check that with 12.2, so I can't tell you whether this has changed. At least up to 12.1, including, this is still the case. So the problem is, as I've outlined previously, if we look at this hash join here, if we are in the second phase of the hash join, in principle, all the data that gets handed over here from one DFO tree via the send and receive operation to the other, from one child DFO to this parent DFO, gets handed over. The actual join could be performed, and any data that matches the result of the join operation could then be sent and handed over here to the query coordinator. That's the way it would work with serial execution. With parallel execution, you have now the problem that you have here a send operation, and you would have here a send operation. If we follow this flow, then these two send operations would have to be active at the same time, because this would still be producing and consuming data in this parent DFO, performing the join. Any results would be handed over to the query coordinator. This is not possible. These two send operations cannot be active at the same time, and therefore Oracle introduces this buffering, this artificial blocking. So rather than performing the actual join operation in this step here, it puts the data aside that it receives here. So in addition to the in-memory hash tables that it has already built based on the data it has received here, this parallel slave set that receives the data now doesn't perform the join, but puts the data aside. Tries to keep the data in memory, in PGA memory, but as you can appreciate, it already has this in-memory hash tables, so it already has consumed PGA. So it's very unlikely that this larger data volume, because a hash join usually operates that the estimated larger data volume will be performed as second row source, because this means the smaller row source will be attempted to be kept in memory here. The larger row source now, due to this buffering, also needs to be kept in memory. And in most cases, this simply doesn't work. So there is not sufficient PGA memory available. So in most cases, this buffering here has to spill to disk. So this is another reason why you have with parallel execution potentially a much higher demand for PGA and temp table space than with serial execution, because due to this buffering, it also means a lot of more work, because you receive all this data, you put it aside. And once this send and receive operation here, this producing and consuming of data is completed, Oracle then basically re-accesses the data buffered. So either if you're lucky, taking it from PGA just, or if you're unlucky, taking it from temp, rereads it from the temp table space, and then performs the actual join operation. And then it can actually activate the send here, because this send and receive operation is then completed. So this is a very important aspect whenever you see this buffered keyword for the hash join, and you also will see additional buffer sort operations in the execution plan which are not there for serial executions. Whenever you see this, this means Oracle, due to this limitation, has introduced this artificial blocking and has to perform this additional work, put the data aside, and re-access it after having consumed all the data. So that's an important limitation of parallel execution. Okay, so if you want to get more details on this topic, as I already said, I have this, for example, this here, which explains in more details this DFO trees and DFO things with the various plan shapes possible. Okay, so to wrap up, I think I've covered, scratched on the surface of all these operations. We have these parallel operations in the data access layer. We have this child and parent DFOs. We have this redistribution of the data, which is performed via these table queues. And one thing that I haven't mentioned is that you can actually use this table queue numbering. You can't really use this numbering here for the DFOs, but for the table queues you can use the numbering in order to understand the flow. So this table queue here and the corresponding child and parent DFOs will be active first. Then the next one will be this O1 table queue with the corresponding with the corresponding child DFO operation and parent DFO operation. And finally, this table queue here will be active, which then hands over the data to the query coordinator. So you can use this number here to get the idea of the flow, because the flow in a parallel execution plan, the sequence can be different than in a serial execution plan. And this comes to this limitation with this buffering and multiple of these pxsend operations not being active, cannot be active at the same time. Well, I've mentioned these DFO markers here, which tell you which operations belong to the same data flow operation. I've mentioned this here, which tells you which data flow operation tree this is about. I've mentioned this here with these different parallel combined with child, parent, and these redistribution operations, and this column here then just tells you what is already there here. So this QZ random hash distribution. So this column basically gives you the same information that you have here. And again, I think it's just there for historic reasons, because before Oracle 10G, you didn't have these PX operations in the plan. So the serial plan looked like the parallel plan, but you had these additional columns which gave you an idea which redistribution methods were used to send the data, exchange the data between the different parallel slave sets. Okay, so I think that's it. I hope you enjoyed this a little bit. And as I said, if you have questions or if you want to get more information, go into my blog and you can ask questions now, of course. And thank you for watching and listening.